Well, welcome to our July um, structural modeling project video conference. And this conference and today basically marks a bit of a transition period in our approach and the work that we'll be doing for the rest of the year. And so this specific report, Technical Report 23, Structural System Structure and Behavior, as an analysis and comments on some of the work we've done over the past 4 or 5 years, introduces one new application area that has been done. A similar type of application has been done before by some people in Japan, and we'll talk a little bit about that. We'll do a little bit more of a classification and talk about a pathway forward. Hello, Janet.
Let's see. Hi.
So what we're going to do is we're going to talk about the structure modeling types. We basically looked at organizing the general types of structure modeling techniques into these 4 areas: classification, ordering, behavior, and everything else. So those are preliminary classifications. The classification and ordering type are fairly solid areas. They've existed since the GMU ISM software had these 2 functions in it. We've tested those, and we've been able to verify and validate the software on those, so they're probably fairly well established. The idea of the classification is you actually have a group of unknown objects. You want to put them into classes. You kind of know what the classes are, so you ask about object A and object B if they're in the same class. And of course, what happens is as you identify objects that are in the same class, then they become a group, and then you say, well, is object C in the same class? Not really, yeah, the same class as objects A and B if they're both in the same class, so that things become, there's less questions asked as the classes grow larger with individuals. So there's a transition between asking questions about individuals to actually asking questions about an individual as it compares to a group, which is a class. Then the strict ordering approach has been verified and validated basically with the logic involved and a certain type of logical configuration. And the ordering are usually irreflexive, asymmetric, and transitive. And they usually have like a global effect. The ordering itself is like not something that happens specifically between just 2 objects. For example, larger than. If object A is larger than object B, then that's really, and object C is larger than object B, then obviously object A is larger than object C. But the larger than really has nothing to do with the interaction between A and B or A and C. It's just a characteristic of these objects. And it's a global type of characteristic measure or metric. And then the behavior area is an area where it's popular to apply behavior types of ideas between 2 objects in a system. One of the cautionary things that we found when we were looking at this and actually producing the software for it was that you really don't have to ask the human group, or you don't have to ask a person to make a decision, because that's just information. If A affects or impacts or causes B, you're not asking someone to rate or rank or put those in order, A and B. You're just asking for information. So in that type of behavior situation, you can actually say, tell me all objects that influence A, or tell me all objects that cause B. And so in that particular scenario, you don't have to do comparisons, and it reduces the number of questions that you have to ask. So that's kind of an efficiency approach, but it's based on the type of knowledge and information that you're asking for. And of course, the fourth category, we put everything else, kind of a catch-all, because there's some other areas that just don't really want to go into right now, but later on we may divide and refine area 3 and 4. And of course, then as we're using the software algorithms and processes, we can either use them in the discovery mode or the design mode. So those are the areas we've covered so far, and we've done and verified and validated the software on the classification and the ordering. And now we'll start transitioning into creating an approach that will support the behavior and everything else. Okay. For the historical and current operational context, much of the work that was done on structural modeling was done back in the 60s and 70s, and the work that Warfield did in 1959, there was a chapter on systems engineering and about specialty types of areas of people using logic to integrate and a system into a larger system. And this was in a book in Analog Computer Design, I believe. And so even in the late 50s, we were talking about using a group social approach to integrate these large-scale systems, which I thought was very interesting. And of course, the structural modeling approach, addresses two primary sources of information: empirical data and logical inference. So you need to be aware of the cost of collecting empirical data and, of course, the cost of logical inference. And this is where this actually gets into a systems engineering problem, because you really want to minimize the cost of getting all the data and information you need. So today, we really want to look at utilizing all the advances in technology and communication and networking that we have available to support these activities of structural modeling. And so we're going to develop a little bit more refined approach in the knowledge management and the knowledge acquisition, and take advantage of the ubiquitous networking and availability of computing power, which was not really available when these techniques were being developed. So then we have the idea of a system structure as opposed to system behavior, and they're related. The system structure dictates system behavior, and system behavior dictates their not necessarily tightly coupled. And really, one of the primary objectives of structural modeling is to actually create and identify an unknown system structure. And when you do that, when that's accomplished, you've encoded a tremendous amount of information just in that system structure. And once you have the initial system structure, it can be refined. You look at from different points of view. It can be translated into different language types of analysis. But creating these initial system structures is an excellent way to encode a tremendous amount of information very quickly. And as we said before, the clustering and ordering are also two kinds of system structures supported by the legacy GMU ISM software. And we, in the methods that we use now and have verified, basically what we do is we use strict order and clustering or equality, things that are equal, combine those in a series to address partial orders. And that's an area where there's been a little bit of controversy in the past, but I think it would be fairly straightforward to separate those out, put them into a natural language type of approach, and translate back and forth between mathematics and natural language in that area. So we've definitely identified that the clustering and the strict order can take advantage of the logical operations efficiencies. But it's not really clear what other types of natural language approaches can do the same thing. So we developed the AMEI, which was the 27 combinations of the 3 logical operators. To look at those and say, well, okay, let's evaluate and classify different natural language concepts and see how they relate to these groups, these logical groups. And then we've identified a couple of interesting parameters associated with that. One is which of the logical groups does the natural language relationship fit into? And then how many logical groups could a natural language relationship fit into? Could it fit into 1? Or could it fit in about 27? You know, what are those parameters? We developed some metrics on that, which we published in some of our previous technical reports. And it's a good metric and a good way to clearly talk about natural language relationships which can cause problems. And one of them we've discussed a little bit in this group is the idea of neurology, where is an object part of itself. Well, you can say, yes, it is in this case, or no, it's not in this case. But using the AMEI, you can very clearly assign the logical operations that go with whatever is chosen. And you can also use the AMEI logical operations to clearly define what you mean by part of. And so that helps reduce confusion and increases precision in our communication about the system structure. And reducing confusion and increasing precision then reduces complexity and normally reduces the cost of developing a specific design from that. So the natural language relationships that we've found that work well with these logical parameters are the ones that are create the collections or the equality, which is reflexive, symmetric, and transitive. Those are the grouping or clustering operations. And then the ones that are create an order, or it's some type of structuring order relationship, which are irreflexive, asymmetric, and transitive. And so these logical groups can be associated with different natural language relationships, but we found that they work fairly well in using logic to reduce the cost by using inference. So then system behavior, we have many examples of people that have used system behavior or the interaction between two objects to create and to do an analysis of the system structure. And in this case, what we find is we have some issues with the logical the scope, because of most of the system behavior types of natural language relationship is just between two objects. You can't guarantee that it goes to all the objects in a global kind of logical field. And these ideas, some of these natural language relationships are causes, effects, aggravate, enhance, support, confirm, weaken, strengthen, influence. So if you have a group of, or a collection of activities, or a collection of objects, or a collection of behaviors, not every behavior is going to cause every other behavior. It's not global. And not every behavior is going to affect every other behavior. So there's restrictions on these. These are just local types of interactions between two objects. So what we found is that when we apply the types of logic that we use in the global relationships, we're not really able to reproduce the results. You can get different types of outcomes. So the outcomes appear to be non-deterministic in these cases. And these are the areas where we're planning on applying some more advanced types of knowledge management techniques to assist in reducing the cost of determining the system structure that's based on these types of natural language system behavior. So the current structure modeling software that we've developed doesn't really support these behavior-based types of natural language relationships well. So what we're going to do is we're going to explore some other areas and see if we can improve that and create one or more types of approaches that will help us incorporate these types of behavior-based. And of course, systems dynamics, is one area that's obviously the causal loop diagrams. And then the causal loops, of course, you can assign equations to those, and you can represent differential equations and so forth, or systems behavior. And so these are an area now where we would want to start looking at being able to include knowledge management and logic associated with those types of systems. And one of the key benefits of interpretive structure modeling, interactive management, has been the establishment of a very well-defined process for knowledge management. It started as in a time where most knowledge management was document-based, paper-based, encoded in information. Now knowledge is encoded in organizational structure. And as we move forward, and as this techniques move forward, the Handbook of Interactive Management is developed to encode and communicate some of these knowledge management ideas. And the general ideas are great no matter what type of, no matter what your medium is that you're working with. So these are very important areas, and we believe that they need to be addressed and curated, and just probably upgraded a little bit to a little bit more computer-based, electronic-based, digital type of information. And given the vast quantities of digital information that are available now, and so this one of the things that's different now in most all industrial and corporate environments is there's a vast amount of digital information available. And so there needs to be a cost-effective approach to acquiring and configuring that information in a way that it can be integrated with the structural modeling and types of activities. So when we, in most of the classical approaches of interpretive structural modeling and their events, they are computer-based, but they're using the computer just for a logical type of analysis. And in this case, what we're suggesting is we're going to develop some unique computer-based modules that will inform the human decision makers and the human group at various times. And so that some of these computing type processes could be running continuously in the background, creating information, notifying people. Before a structural modeling event or some type of decision event, they could gather the relevant information at that point in time, analyze it, package it up, present it to the decision makers, or they could do it in real time. Those are the types of activities we have available now that weren't really available in the 70s and 80s. So we're going to be looking at some general areas and evaluating these and for inclusion into our next set of work. And one of them is the computer-based learning systems with emphasis on the Theme 1 program developed by John Aubrey. This is a very interesting approach, and it's basically a software system that's used for learning arbitrary formal languages and modeling arbitrary formulas and propositional calculus. So one of the things that could be done here, we're talking about systems that are operating in the background. The system like Theme 1 could be used to identify languages, interfaces, formalisms that are not obvious in large volumes of data. That could be running in the background. Just use computing power, so that's fairly inexpensive. And then also looking at the logical format and the logical structure of whatever these arbitrary or whatever these structures are that are being determined on the information. That's an area that we've been working on recently, just getting this Theme 1 documented. We'll continue to work in that area. Then the union rule configuration fuzzy logic approach is developed by William E. Combs that focuses on union rule of the eliminating rule explosion computer-based reasoning systems. Bill has done quite a bit of work in logical rule integration in the area of fuzzy logic or integrated multi-valued logic. One of the interesting things, the connection between Theme 1 and the union rule configuration is the differential logic and the basically a triadic approach that John Aubrey uses in looking at the change in logical outcomes. And in that differential movement across some logical plane or some area, basically then seems to relate very well to the idea of a fuzzy logic type of a fuzzy number, which is also two-dimensional. So there's these two-dimensional constructs that are used to represent the value of any logical rule set. So theme 1 develops them, union rules used to evaluate them, so, and also to present them to human decision makers in a different format. And then there's constraint theory that was developed by Jared Friedman, which is focused on internal consistency and computational allowability of any mathematical model. And so in constraint theory, what we have is again, a large organization's tremendous amount of information. In this case, the information has been reduced to mathematical formulas. So it's been put into a formal language. And usually those formal languages are developed by different groups, little tribes within the corporation or within the engineering or technical groups. And large-scale engineering and large-scale integration has to take these bits of formal statements about the system, bring them together and see whether or not they're internally consistent and computationally allowable. So it's a very interesting area, and it starts to make the connection between informal natural language and formal languages, expands it a little bit. We're going now a little bit more just away from formal logic and into some of the mathematical, some more other types of mathematics, put it that way. So we did an analysis of the constraint theory. The first example of low dimension, and we'll look at that here in a little bit. But essentially, this is interesting because in this example of low dimension, we run into some uncertainty. And so constraint theory is designed to reduce complexity. And one of the ways you reduce complexity, of course, is to reduce uncertainty. And when we looked at the first example here, as we'll go through here in detail a little bit, is that we had the number of variables and the translation of the equations with some uncertainty because there appeared to be some variables that were not being accounted for. And then there was some interesting configurations in the equations. We had one variable that was both a linear equation as well as a nonlinear equation. And so these mathematical representations, from a formal mathematical standpoint, raise some issues. And to address these issues, we just use the structural modeling approach with the natural language relationship dependent on it. And again, this natural language relationship has the following three attributes. It's irreflexive, asymmetric, and transitive. That fits into one bucket. And we're saying that it's essentially in a global type of natural language relationship. And in doing that and assigning it a global relationship and giving it irreflexive, asymmetric, and transitive properties, it fairly well defines the application of the natural language relationship. So what we do now with that is we just go through and create a dependency tree, and then that creates another structure. So we have one structure of mathematical equations that are based on the mathematical rules. And now what we're doing is we're looking at it and saying, okay, we're going to now have a natural language relationship that says depends on. And when we look at the idea of multidimensional mathematical model management, we could think about it saying, okay, we're going to do multi-dimensional Lego block management or multi-dimensional concrete block or brick or whatever. So that the idea we have a mathematical model, that's the object that we're managing, but it could be multi-dimensional X management. So we're just looking at these equations as a general type of object with natural language. And so what we found here again was that we had two unlisted variables, D max and X, and then of course we had one constant that wasn't assigned, so we just set that to 1. And then we went through and just answered the question, drew the picture for dependent on. And now this creates a dependency tree, which is a different structural model of this group of equations. And we looked at those, and it really, the dependency tree gives us a wealth of information. And what we find here, is shown in this graph, and that's that the top level metric is directly dependent on P, which is circled in green, and E, but E itself is not primary. E is composed of M, A, D, and D max. And the ones that are circled in green are the terminal variables. They don't depend on anything else. And then we can see it also depends on C, which depends on S, which depends on X, which is terminal. Well, when we go through and look at this structure, we see that actually E, D, C, and this tree is just recursive. And so essentially what what's clear now, just by looking at this picture, is that the constraint, the computational constraint, is associated with the recursive variables, and the allowable computations are associated with the variables circled in green. So this is a rather non-standard approach for structural modeling, but I believe the people in Japan also have done a similar type of structural modeling, but they've done it with a different structure. They've done it with the structure of the human body and all the information that we have about the connections and the way the human body works. Much like we have a tremendous amount of information about mathematics and the way that series of equations and the way that we represent mathematics formally, the way that works. But when you have a system, human body, that's working correctly, the structural analysis of that is not really going to give you much more information, if any. What they use the structural modeling for in the analysis of the human body in Japan, it's my understanding anyway, is how to engage that system when something's broken. So when someone has a broken arm or a broken knee or a foot or some type of issue where that system is broken. So they use this technique to analyze it and say, okay, what do we need to do first, second, third to go through and rehabilitate the structure back up to its to the best it can be? How can we actually rehabilitate and fix the system. So in this particular case, it's rather similar, and that depends on natural language relationship. There could be others that we use for mathematical equations, but many, if not all, of the unaddressed mathematical issues that we talked about in the example of low dimensions are just not important in the structural modeling natural language analysis, because it is not following the rules of mathematics at this part of the analysis. It's following the natural language concept it depends on, and that's it. And then you draw that structure. So what to do about the missing variables? Well, there are no missing variables because you account for each one of them in this case. How to apply the concepts of the degrees of freedom, because you have a linear and nonlinear equations that both point to the same variable. Well, that basically doesn't matter in this case. And when we work through these, all of the questions that are associated with a formal language in this step just basically disappear. And we're able to then give an analysis that shows a different type of mechanism and methods, but essentially gives the same answer. But what we find in looking at the answers is that we really couldn't, precisely determine what those were because of the missing variables, and then the idea that one of the factors wasn't decomposed to its final fundamental concepts. Another interesting thing is that with a formal language like mathematics, it seems that a program like Theme1 should be able to contribute to the evaluation of a large set of equations or constraint theory models. So that's kind of one area that we're going to look at a little bit once we get Theme1 into a little bit different construct. But it should be able to, we believe anyway, assist us in some of these types of analysis. And we're looking at a development of an open source, modular, web-based, multi-user, configurable knowledge management system that will really support the complete range of structural modeling activities. And we have the ISFR and the ISSS are really looking at having a new book series where they talk about not being completely dependent on mathematics. And so what we're hoping to do here is to demonstrate by example natural language relationships that are directly isomorphic to structured graphics, which can be displayed graphically and understood graphically, and are isomorphic to mathematics. So that what happens is you can engage any one of those languages, either the prose or the structured graphics or the mathematics, or a combination of them, depending upon what you're familiar with. So that's kind of our goal in this case, and we believe we kind of laid the foundation for it, and it should be interesting to see how far we're able to go down that road. So basically what we're saying is that structure and behavior are primary characteristics. They're related in certain ways, and we really need to be able to have more focused, verifiable types of analytical processes. We've presented an example here, of course, that shows a new type of application of the ordering step, the irreflexive, asymmetric, and transitive. The restriction of using these specific types of natural language relationships on, on behaviors like causal loops or influences are offset by being able to actually apply them to the equation sets in the way we've shown here. And actually, we believe we should be able to balance these in a way that supports more efficient evaluation of very large-scale systems. So that is basically the overview of what we've done so far. Are there any questions?
Very interesting. I'm glad you're going in this direction. We had actually forgotten about the Friedman book, and we briefly thought we might have lost it. We found it again, but yeah, we only got a bit into that because of his idiosyncratic language that we had. We struggled a bit getting through what he was talking about there and his presentation style. So it's good to see this. I think it would definitely help explain his method if you see his examples in the in this method with the not the bipartite graphs but the direct graphs. That's a nice clarification. Also, computationally allowable. I don't know if you have a alternate phrase for that, because he, that's so important to what he's doing here, and we hadn't heard that exactly like that before. So I thought maybe I don't know if something else could be brought in for that.
The well-formed equations, the well-formed formulas, those are phrases and issues, from mathematics that are very important. You can.
Those are right. Those are more familiar. Well-formed or well-posed,
right,
rather than computationally allowable. Yeah. So I think that for some reason the computationally allowable seems it starts me thinking about things that are irrelevant, whereas the well-formed and well-posed keep one focused on the equations.
I think that's a good point. I think we'll think about that.
Yeah. The other question was about the ISM side and the let's see, you referred to a technical report 0012, I think. And which I think when we import those we change the name, so so I was having trouble finding it. Which one would that be?
Well, okay, so let me go ahead and
oh, is it in the bibliography? Maybe I should have looked there.
Well, let's check.
It's the one called Defining Structuring Relationships.
Okay.
It's 28th.
Great.
There it is, Defining Structuring Relationships.
Right.
August.
Okay, very good. So what I was wondering about in that is the issue of all of those types of relationships being not well posed from your perspective, I was wondering about Warfield's use of um, the of Harari's theorem,
Mm-hmm.
and does Warfield take for a natural language relationship which um, does not, let's see, is not reflexive and transitive the way Harari's theorem requires.
Yep.
Does is their approach to, or is Warfield's approach to find a related natural language relationship that would satisfy those constraints, and then do a computation on that related relationship, and then go back and interpret it in light of the original relationship?
Wow. Okay. So there's a lot of stuff there.
Yeah.
Let's see. So let's let's okay. So if we go back and look at the AMEI, if you can remember the three the hierarchy, the network, and then the combined hierarchy and network piece,
Mhm.
right?
Mhm. Right.
So that kind of has some of the real basic general concepts there. And even here in this particular tree, when we did this tree, one of the things we did here is that we did not do in our other trees is that we actually repeated. So we got D
Right.
and D and D. Well, you could have a cycle that goes back, but I just decided not to do that because I wanted to go with the steps, right? It's
Right.
easier to show the steps that way. Step one,
Mhm.
step two, so forth. And I think that in this particular algorithm, um, and and connecting back to what you talked about with computationally allowable, um, I think sequence is important.
Mhm.
Sequence is also that's went back to the work that Stewart did when he first started doing design structure matrices way back when, cards and Fortran. When he was looking at these graphs, it was a stepwise approach.
Mhm.
And in the idea is, in many of these cases, is that either way will work, but one is much more efficient and much
Mhm.
more economically valuable than the other.
Mhm.
So, so that, and that was the, the whole point of Stewart's work, I believe, when he first started, was computational efficiency,
Mhm. Mhm.
necessarily computational allowability. And I think that um, there was a Society of Applied Mathematics and Society of Applied and Industrial Mathematics, two uh, papers, one that was written by Stewart and one that was written by Warfield. And they kind of, I believe they referenced each other, or Warfield referenced Stewart. But what happened there, I believe anyway, if I remember correctly, was they changed they were both talking about their matrix forms, but they had the equations in different standard forms.
Mhm. Mhm.
And so um, I think a key to thinking about this computability when we're talking about equations and certain kinds of equations is to look at those specific examples and then see if there's similarities between them.
Right. Right.
And one of the areas I think that became important is a differentiation between the natural language logical operators that Warfield was using to guide his stepwise work. And Stewart didn't appear to do that. And so I think that and searching for a computational allowable configuration within his equation set. And I haven't really looked at how that would match to this.
Mm-hmm.
But it might.
Mm-hmm.
You know, so and that would kind of clean up some of that too. But that was something that I just haven't looked at recently.
Right. I think it would help to see the graph with the cycles as well as the graph laid out stepwise. That's illuminating.
Yeah, you can. Okay. This way we just did it this way because I think that it may, well, we'll see. Yeah, because if you use cycles, there might be other forms of equations where it's not clear how you address it. Let's say, for example, you had an equation set that didn't do this repetition, but you had certain terminal variables in step 1 and step 2, and then the other terminal variables in like step 6 and 5 and 6, right?
Mm-hmm.
But none of them are repeating, right? And so that's a different type of constraint. So anyway,
Mm-hmm.
that really didn't show up here. This is just
Mm-hmm.
one example. But yeah, but either way, I think it's easier to show it stepwise first anyway.
Mm-hmm. The Design Society, I noticed, has a has a conference on dependency structure matrices. I don't know if you're familiar with that, if you've maybe even attended before, but it is. We were wondering about going just to get a sense of how they talk about the whole field and whether there's standardization. You know, is there movement towards standardization, clarification?
It's yeah. So I went to a couple of industrial conferences on DSM, sponsored by a very large international industrial organization. And one of the things that was the most interesting was at that time anyway, was the difference in the specific approaches. And now what I see in DSM, and this thing that popped up into my head when I first saw what they're doing, right? And way back when I was first wondering about reverse Polish notation, right?
Mm.
I think I had a HP 41 or whatever it was way back in the day, you know, that had reverse Polish notation.
Mm.
And I just it just wasn't sitting right in my head for some reason. So I went from picking up the calculator, I went to the library, jumped in the library and said, "Give me a book on reverse Polish notation," right? And engineering library, I found one, I checked it out, it's going to scan it, make sure I understood what was going on. And in that book, in the reverse Polish notation, what they did was they had listed sequentially every combination of a series of, you know, simple equations, addition, subtraction, right? Just done it over and over, and, you know, just changing one variable, right? And giving the answer page after page after page after page, right? There was no real integrating analysis or combination of what's going on, right? And I, from what I see right now, there's a DSM community is kind of was coming up with these specific examples that are kind of don't have an integrating type of approach.
Right.
One of the things that I haven't focused on recently what I did focus on before I went into looking at this logical piece and doing the ISM software was the idea of clustering and the idea of a total system metric. And so what we're doing here is we're talking about metrics that are between two objects, right? Or between, basically we're asking questions and we're talking about, oh, this metric or this relationship is between these two objects. But if we, in design structure matrices and in structural modeling, when you do the space-based approach like Warfield and Christakis talked about back in the early, I guess it was maybe the middle 80s in their dimensionality, then what you want to do is you want to bring all of the objects within a space you want to meet some criteria. You want to either minimize some factor or metric between all the objects or maximize it or whatever. So I haven't seen anyone that uses the dimensionality or the spatial type of work that Warfield and Christakis outlined.
Mm-hmm.
According to Kevin, they outlined it. They did some academic examples, but then they never really used them because it was too complex for their system. Basically, at that time, is my opinion. What they were doing was good enough, right? But so I believe the ideas were in dimensionality for DSM were introduced then. We didn't do it, and I've approached that, and some of my earlier papers of IEEE and other places, I gave some very simple examples of how that works, and it's but it's kind of it's kind of a set of special one-off cases in a way.
Mm-hmm. Right. So that's why we were thinking of even going there, because we'd like to confirm that, at this point in 2018.
Mm-hmm.
I'm looking at the information on this conference in Italy in October.
Yeah.
And they say the topics include research trends,
Mm-hmm.
systems engineering, system dynamics, general system theory, and others.
Oh, yeah.
So they're...
Well, they have a conference in Paris every year, too.
Mm-hmm.
And there's conferences, they like to get together and talk.
Right.
Which is good. But I'm...
Is that for the Design Society, do you know, or...
Oh, this is the one in Paris is specifically for DSM.
Okay.
Yeah.
Mm-hmm.
And it's
we met some people. We met the president of the Design Society and a few colleagues in Corvallis at the NSF design workshop in March.
All right.
That was on systems engineering. What do they call it now? The NSF section on system science, design and engineering, or something like that. So there were quite a few people from the design community.
All right.
I really like your split, and was that something that Warfield did, the design discovery?
No, the idea with the design and discovery is just came more from really it came more from the work that Brian Marr did on functions, analysis, architectures, and tests, right, or answers and tests, right?
Mm-hmm.
So if you take that type of high level containerization, then if you're going to design something, you're going to start with the functions, right? And you're in control of that because you are designing whatever is going to be done. right?
Mhm.
In the discovery mode, right? You really are your job there is to discover the architecture, right?
Right.
So
That's right.
what is the architecture? What's going on? How do these things interact? What are the objects? What are the relationships? So that's kind of where that came from.
Right. Yeah, I like that. In my father's work, it was called systems identification, um, and but I like the idea of splitting into two basic um, modes of inquiry or areas of concern. Um, one can continue proliferating cases, but different kinds of uh, inquiries, but those two seem to be that's a really robust um, distinction. So I like that. I also like your the mathematical relations and natural language relationships. And I think when you promoted that recently on the Ontolog forum, I don't think people grasp the subtlety of what you were saying there. That those two, the form of the word relation should be reserved for the two separate cases. But that's worth continuing to push for.
Yeah, I think we'll keep. Yeah, there's a lot of area here that just kind of keep going. I'm really interested in Aubrey's work.
Yeah.
I think that'll be a great addition,
Mm-hmm.
and I'll try to bring some of these other aspects together. So for August, well, first of all, for July 21st, we are on the road, and it's my annual electronic detox week. So,
Yeah, we're traveling on that day.
so I think the 21st, I think will probably be a non-event,
Mm.
and then for August, I haven't had anybody step up to say they'd like to do August yet. So that August 4th, because we will not be doing August 4th, we'll be doing September 1st. So if anyone else would like to do that, be sure and let me know. But
so I missed the beginning. Is Kevin not participating for a while, or
well, Kevin is not on today. I haven't heard from him. I don't. I'll send him a note and see what's going on, and see what he's doing. And but it's I'm not sure. I think he's pretty much engaged in doing the playbook with
that's right, right.
getting that ready for the folks in Europe. He said they had half a dozen events, so he'll probably be busy. But
Right.
I'll ask him directly. So with that, we'll kind of shut it down. I hope you have. Are you going to be going to Corvallis?
We are, but only for a few days.
Okay. Well, maybe you can tell us what you thought, what you found out.
Right. Let's see. The 4th is probably not good for us. Maybe the 18th is better, but we'll all be in touch.
Okay. Sounds good to me.
Very
Take
good.
care. Have fun.
Thank you. You too. Bye-bye.
Thanks, Janet.
Bye-bye.